In classic software-defined networking, in fact, in networking, period, there are three levels of control and management, and basically the definition of what networking is that's shown here. On the very top is the management interface. This is where a network engineer, like a CCNA, CCNP, or CCIE, would normally access the system through CLI, sometimes through a web interface. This has direct control to the control plane. Now, the control plane's job, primarily speaking, is to actually take various inputs and create a forwarding table. Now, the forwarding table goes by a number of names. If the forwarding is at layer 2, then the forwarding table would be a MAC table. If the forwarding table is running at layer 3, then it would be called a routing table. But in the way we're studying this right now of pure computer science, we simply refer to it as a forwarding table. And a forwarding table can actually be more complex. It could be looking at port addresses, it could be looking at time of day, it could be looking at load balancing information. A lot of things could actually be applied to a forwarding table. So let's take this diagram and break it down as we would see it in a network. So in a network, if we have, let's say, 4 switches here, that would be 4 layer 2 devices, then the data plane would actually be forwarding based on MAC tables. And those MAC tables, incidentally, would not be filled out by the data plane. The data plane relies on the control plane, which we don't even see in this picture, to fill out the forwarding tables, so that when a packet would arrive into the data plane would check a forwarding table. Based on what it sees, it would know how to forward that packet out the appropriate interface. And then the same thing would apply if ultimately the destination is some device over here like this. You would see the forwarding table being referenced in that particular case 3 times until the packet actually arrives where it needs to. Now let's add a control plane. When a control plane is added on top, we have the logic which allows these control planes to actually talk to each other. Normally in full mesh in a lot of designs, the control plane actually uses the data plane for the control planes to talk to each other. But it's important that you understand that the control plane is the brains that sits on top. Almost always, when you talk to networking people, these two things, to them, are the same thing. And depending on how long you've been in networking, those two things are the same thing forever. And adapting to the concept that in some way, shape, or form, the control plane is removable, that it's attached somehow with Teflon tape, and you can just rip it off like Velcro or something, is completely foreign. But that's what is going to happen. In fact, it's in the process right now. And here's why. Right here we see 4 separate control planes. Each one of these control planes is thinking on its own. It makes up its own mind based on what it feels like. And hopefully, if the protocols are done perfectly, and quite frankly, it took many years to get the protocols perfected to the point that the conclusions which control plane number 1 creates actually work in harmony with the conclusions of number 2 and number 3 and number 4, because they don't have to. In fact, these control planes can get out of whack and all kinds of fun, glorious, terrible things start happening, like packets start just circling around back and forth because the control plane filled out forwarding tables incorrectly, and you wind up with routing loops and then all kinds of fun things that you have to fix. Well, it turns out that we should give a lot of credit to the fact that this was not easy to get control planes to all think together. This is called distributed computing, and it is the most complex kind of programming that there is. But this guy came along, Martin Casado, and he was challenged with the concept of what would the internet look like if you would completely redesign it. And what he came up with was a result that, well, it made him a billionaire, but ultimately he never saw it coming. Because what Martin learned was that this data plane part was, he was not able to improve on it. It was amazing. Then he took a look at the control plane. Now, he's not a network engineer. Let's be clear on that. He's not even a CCNA, right? And he's looking at this control plane stuff, and he's saying, wow, this is hard. And he studies it some more. Wow, this is really hard. And studies it even more. And he said, this is beyond hard. This is an impossible problem for me to solve. And when he went and looked at vendor-specific protocols that could sort of provide an application program interface to control the control planes, because he wanted to take control of the control planes. And you don't do that with control planes in the traditional sense. They think on their own. And if you get in there, you get in there with a CLI on a vendor-specific way in order to configure the control plane, and then you would have to go to these other guys and hopefully configure everything that it just works. He said this is way too hard. And what he decided was that the vendor-specific protocols are an absolute nightmare to automate it with software. And if you look at SNMP, while that might be great for monitoring for problems, it's a horrible interface for programming. Just maintaining the MIBs and working into it was a nightmare. Bottom line, he's trying to develop a cool app, a square peg that just, no square holes. All the holes were round, nothing fit. So the decision was, well, if this is the case, then I'm going to assume that the entire design is just wrong. But in a sense, what he was really saying is, I'm going to leave the data plane design as it is. But this control plane, I'm throwing away EIGRP, BGP, OSPF, and bridge protocol data units, and STP. And it just, he said, that doesn't work anymore. Because it turns out that if I develop my own protocol, and ultimately OpenFlow was born, he said, I could take a single controller and I could devise some primitives to fill out instructions to maintain the forwarding table at a central point. Now, at this point, it became clear to Casado that it is no longer rocket science to make sure that all these data planes see the same forwarding table. I mean, if you think about it, all those data planes that you see right there are being directed by a single brain. And the part that was most difficult, insanely difficult, which would be to get all of these brains thinking the same thoughts, was a non-issue if you have a single controller. Now, once upon a time, when we used to think that these links, which ran at 56K, were fast, we thought like this. But links run at least a gig or more. So suddenly, the notion of removing the controller from the data plane itself actually becomes, should have been obvious for quite some time that this would be the right way to go, actually. So now we have a software developer who wrote an extremely cool set of primitives that's able to direct the data plane. And this is where it really gets interesting. The data plane is no longer restricted to be just a switch or a router or a firewall. It's everything. That's, well, switch, router, firewall, load balancer, VPN management, you name it. It does it all, and it does it incredibly efficiently. And people are becoming billionaires because they're hopping on this idea. So what is happening is that this data plane basically becomes incredibly stupid, and it takes its instructions from a central brain. Now, obviously, the speed of light distance between here becomes an issue, because when it comes right down to it, you have to write software right here in order to get instructions down to the data plane so that when a packet comes in, If the instructions are not clear, the data plane doesn't know what to do with it, it generally has two options. The classic approach would throw it away. I mean, that's the way it would work over here. If a packet arrives and the instructions are not adequate to describe how to forward it, the data plane does not get a chance to make up its mind right there on the spot and say, gee, which way am I going to send this packet? It's too late. That had to be figured out ahead of time. So it's simply discarded. But when we go over here, there's an interesting twist. If a packet shows up and the data plane's not sure what to do with it, it can cut off the header portion, not the entire packet, just the header portion, and send it up to the controller and say, what should I do with this? And on the fly, the controller sends the response back and says, by the way, attach this header back to the rest of the data that you have and send it like this. Don't ask me about that anymore. Make a note that from here on out, forward information that looks like this out some appropriate port. So information goes that way. That's an interesting approach that actually is unique to software-defined networking. You would never see that in the traditional sense. Now, personally, I believe the best software would be code that would actually load the data plane with rules so that when packets come in, there's no need to go up and reference the controller after the fact and say, what do I do? The instructions would actually be stored right here. And off the information goes to the right direction. So then what we wind up with is a diagram that looks like this. Our data plane, these are no longer routers or switches or load balancing or firewalls. They're just referred to as open flow switches, even though they do everything. And the notion of, oh, that's a firewall, or oh, that's a switch, or oh, that's a router, that's gone. So what we have then in our controller is a southbound portion, most likely speaking open flow, perhaps OpFlex. But if it's going to be a pure software-defined network where the data plane is completely separate from the controller, it'd probably be one of those two protocols. The controller portion then, which is actually being concerned with the topology of the network and maintaining the current state of the network is what the controller would do. And then the northbound interface presents an interface to applications, almost always a RESTful interface. And what it does is it offers a declarative method for applications to send their wishes to the controller, and then the controller manifests that into whatever needs to be done to the forwarding plane, so to the forwarding tables out on the data plane, and the information is carried out, typically in microseconds. It's incredibly fast how this works. All right, that's it, Bill.